Okay, so in the last class we left here. Basically, we had discussed these graphs that for a filament lamp, your graph will seem something like this, and for your diode, your graph is going to seem something like this, because diode allows your current to flow in only one direction, right? So if current is only flowing in one direction, we know that R equal to V upon I, and we know that I is inversely proportional to resistance. So resistance is very high in the forward direction, and resistance is very low in the backward direction. Okay, then these are all the graphs that we need to know about. Ohmic conductor, always straight line. This is for a semiconductor diode, filament lamp, thermistor. We need to discuss this thermistor. Basically, in our syllabus, we have negative coefficient thermistor, and we have that coming up. Okay, then resistance of a metal wire. So basically, when you're going to talk about resistance, what is resistance first of all, right? You should know how to define resistance, and we know that R equal to V upon I. We can always write that resistance is a ratio of what? Resistance of a ratio of voltage across a certain circuit component over the current passing through it, right? So that is going to be our resistance, right? And then another thing is that we need to know about our resistors, which we discussed yesterday. We need to know about our variable resistor, and which is also called a rheostat, and our fixed resistor as well, right? So all of these things we discussed yesterday, right? So now we're going to continue from there. Okay, right. Now, talking about in today's class, basically we need to talk about resistivity, right? Now, what is resistivity? Resistivity is basically going to be like it is not exactly no, it's not the same as resistance. Resistivity is basically a property of the material that is independent of the dimensions of its material, right? So basically, when we talk about resistance is going to be dependent on three things, right? We already discussed what resistance was. What was resistance? Well, I already told you that it was the ratio of the potential difference V across a component to the current flowing through it. We discussed about variable resistor and fixed resistor. Fixed resistor is going to have a resistance of fixed value. Variable resistor is going to have a resistance that can be varied. We discussed how we can measure resistance. We know that R equal to V upon I, so we need to measure voltage using voltmeter, and we need to measure current using ammeter, and then we're going to draw a graph, and the gradient of that graph of VI graph is going to be what? It's going to be resistance, right? And then we also discussed Ohm's law. We also discussed Ohm's law that says that current passing through a metallic conductor is directly proportional to the potential difference across it, provided that physical conditions such as temperature remain constant. And we discussed also that why are physical conditions important? Because as temperature is going to increase, the resistance of the filament lamp is also going to increase, right? So basically, resistance has a relation with temperature. That is why Ohm's law is only applicable when physical conditions are, they do not change, basically, right? Now moving back to today's topic, right? Resistivity. So I just told you that it's the property of a material that is independent of the dimensions of the material. Basically, resistance is going to be dependent on three things, right? First of all, we have length, we have cross sectional area, and we have type of material, like it's written here, right? So for example, okay, first of all, when we talk about length, resistance is going to be directly proportional to length. And I told you what I mean when I'm saying that it's directly proportional to length, meaning that when resistance is going to increase, when length is going to increase, resistance is going to increase, right? But it's inversely proportional to cross sectional area, right? So when it's inversely proportional, that means that if your area is going to, if your area is going to increase, so resistance is going to decrease, right? So how can we write both of those relations? Wait, basically we can write those relations like this, right? And when you're going to combine it, it's going to be like basically R equal to K, and because this L is in the numerator, it's going to come in the numerator, right? And then in the denominator we would have area only, right? This is how your formula is going to become, right? Now this constant, which you can see, basically what happens is when you are making a formula, right? Right now, before making the formula, we only had proportionality sign, right? When we remove the proportionality sign and we combine the relationships into one, and we combine the relationships into one formula, when we remove the proportionality sign, that is replaced by an equals to sign, and a constant also comes in, right? Now, because I was already talking about a constant here, we know that resistance of a conductor depends on the type of material it's made up of, right? That's one of the things it is dependent on, right? So the constant here is resistivity, right? And I just told you what is resistivity, right? So the formula altogether is going to be something like this, right? So this R is resistance, right? It's going to be in ohms. And your P is your resistivity, which is basically a fixed property of the wires material, and it's going to be in ohm meter. L is length of the meter, which is again going to be in meter, and A is your cross sectional area, which is always going to be in meter square considering SI units, right? So this was all about our resistivity, right? Yes, I think this is all about this. Now moving on. Okay, so for this we have electric circuits. Now circuit diagrams and circuit components. So basically for your syllabus you need to know certain symbols and you need to know what they mean whenever you see them, right? So cell we already know, it looks like this: battery, power supply, DC power supply, AC power supply, fixed resistor, variable resistor, or you can say rheostat, thermistor, light dependent resistor, heater, potential divider, transformer, magnetizing coil, switch, earthing, which I just talked about in the last class in electrostatic induction, right? Basically, and then junction of conductors where your two wires are meeting, for example. Then we have lamp, then we have motor, generator, ammeter, voltmeter, diode, light emitting diode, fuse, relay coil, right? And then you need to know a little bit about all of these, right? So we'll be discussing all of them. Okay. Now power supplies, we know that cells, batteries, power supplies, generators, all of them are going to supply current to the circuit. When we talk about resistors, potential dividers, fixed and variable resistors, thermistors, light dependent resistors are called LDRs also, and they are going to be used to control current. And when they're saying that they're going to be used to control current, we know exactly why they're going to be used to control current. Why? Because we know that basically if there are they're resistors, right? And we know that R and I are related because they're inversely proportional, right? So when they're going to have a high resistance, current is going to be low. When they're going to have a low resistance, current is going to be high, right? Now if you talk about what exactly a potential divider is, potential divider is basically a line of resistors connected in series, right? And what it does is that it provides a fraction of the voltage of a source to a part of a circuit, right? So basically, if definitely if you talk about a circuit, it is going to have a source, and that source is going to have a particular voltage, right? Now what the potential divider is going to do, that the potential divider is going to divide certain voltage from that source to a part of the circuit, right? That is what it's doing, right? And we're going to discuss it in detail. Okay, then we have fixed and variable resistors, which we kind of discussed. We know that variable resistor is also called a rheostat, and yes, that's it. When the resistance is going to increase, the output voltage is going to decrease, because we know that resistance and voltage are basically we are going to discuss another formula for that, so let's leave it for now. And then we also have another type of potential divider, which is called a potentiometer, but it's not written here, so let's leave it for some time. Meters, we have ammeters and voltmeters. They're used to measure the current and potential difference. We know that ammeter is always going to be connected in series, voltmeters are always going to be connected in parallel. Then we have electromagnetic components, magnetizing coils, relays, and transformers use electromagnetic effects. Relays are going to use a small current in one circuit to switch on a much larger current in another, right? So basically need to know these small uses that relay is using a small current to switch on a much larger current, right? Magnetizing coils, relays, and transformers use electromagnetic effects. Transformers we'll be doing in detail. If you need to know in one line, then they're going to step up or step down current and potential difference, which means that they can either increase it or decrease it, right? Then we also have fuses. They're going to protect expensive components from current surges and act as a safety measure against fire. This we're going to discuss in practical electricity. Then we have diodes. Diodes is limited to this chapter only, so we're going to do it in a little bit detail. So this is the symbol of a diode, and diode is basically going to allow current to flow in only one direction, right? So if the diode is connected to an AC power supply, it will only allow current half of the time, because we know that your AC is constantly changing direction, right? So what will happen that it will only allow a current half of the time, right? And this process is going to be called rectification. Just don't need to no need to go in detail. This is all you need to know at this stage, right? Then variable potential dividers. When two resistors are connected in series, the potential difference across power source is shared between them. Okay, now this part is what I need to discuss in detail, but before I do all of this, I'm gonna start with simple combinations, right? So now let's actually start with today's learning outcome. So basically I'm gonna start with simple circuits, and then I'm gonna move on to potential dividers and all of this stuff, right? So basically, first of all, if I give you two circuits, wait, let me bring two circuits first. mm, okay, there we go. We have a series. Okay, so right in front of us now we have two circuits, right? One of them is parallel and one of them is series, right? So first of all, when we talk about what exactly is the difference in between a series circuit and a parallel circuit, right? So a series circuit is always going to have only one path through which your electric charge can flow, or electric charge is actually current, right? So first thing that we need to talk about is, of course, our current when we're talking about circuits, right? So first thing we're talking about here is current. Okay, so when I'm talking about a series circuit, in a series circuit, current every point will be the same, right? This is the first thing that you need to know about, right? Now, okay, let's do one thing. Actually, let's first do all for series circuit and then for um parallel circuit. Right, so this was the first thing, that your current at every point will be the same, right? Now talking about potential difference, right? So for a potential difference, what is the thing? That the sum, why is this, the sum of the potential difference across each component is equal to the potential difference of the whole circuit. Now, what exactly does that mean? Basically, we know that the potential difference across the whole circuit is going to be basically we know that the potential difference across the whole circuit is equal to the sum of the potential difference across. Basically, if I take a circuit C, wait. So if I take a circuit like this, that I have a power source, I should have gone somewhere else. See, I have a power source. I have a voltmeter right here. This is my voltmeter, right? And then I have two resistors. And across them also I've connected voltmeters. So voltmeter number 1, voltmeter. Right, so this is kind of the rough idea what I'm trying to show you, right? So the idea here is that basically if we talk about the EMF of the source, see, voltmeter 1, right? If this is voltmeter 1, what is it measuring? It is measuring the EMF of the source. Why is it measuring the EMF source? Because it's connected in parallel. Because it's connected in parallel with the source, right? So it's going to measure the EMF of the source, right? Then we have this voltmeter connected in parallel to this resistor and this voltmeter connected in parallel to this circuit, right? So what we're going to do is when we're going to have V1 value and when we're going to have V2 value, when we're going to add both of these values, we're going to get the value which this voltmeter is showing, right? So that is the idea of potential difference in a series circuit, right? Then talking about resistance in a series circuit. Why was it a series circuit? First of all, because see, there is only one path for current to flow, right? Not considering voltmeters. Voltmeters are not going to hinder the current flow, right? See, it's gonna flow in one path only, right? Then the second thing is considering two resistors that are connected in series, right? First of all, how are resistors going to be connected in series? Something like this, right? So current has only one path to flow, right? Now we know that the current that flows through R1, for example, this is my R1 and this is my R2, is going to be the same, right? Because we know that they're connected in series and current at every point in the circuit is the same, right? Another thing that we know is that basically your if we talk about voltage, basically we have two resistors, right? Now each of these resistors is going to consume some voltage, right? And for example, the voltage this is consuming is V1 and this is consuming is V2, right? So I know that my overall voltage, basically what I know is that I know that my voltage is going to be equal to overall voltage is going to be equal to V1 plus V2, right? That I know, right? And I know that all of them have different resistance. I don't know, right? So what I'm gonna get is that I'm gonna get that basically V can also be equal to its respective formula, right? So it can also be equal to I am not gonna give I1 because we know that current is same, right? So I R1 plus I R2, right? And it keeps on going on, right? So what I can do is that I can take out my I common because it's the same, right? So I can take out my I common. So now what I'm gonna have is my R1 plus R2 only, right? Now I know that my voltage is also equal to the overall resistance and the current is the same again, right? So I can also write as R and then this is R total and this is equal to I, again the same thing, I R1 plus R2. Now if you look at this, because I on both sides is the same, it's gonna cancel out. So in the end, we're only going to have this thing left, right? So this is how, current in a series circuit is going to work out, right? And this is how, things are working there, right? So I can say that, first of all, let me erase this. In a series circuit, the effective resistance R is the sum right. So this is it for your series circuits. Right now we have parallel circuits. Okay, so now let's try to imagine what's gonna happen. Okay, so first thing that I need to know is that if I'm talking about a parallel circuit, then parallel circuit, okay, more than one path for electrical charge to flow, right? Okay, this thing. Now the first thing that you need to know about is that the sum of the individual current in each of the parallel branches. Let me first write the pointer and then explain. Is equal to the into or out of okay, give me a minute. Okay, right, so this thing. Okay, now let me explain you this thing. Okay. So for example, again, I have a power source, and I have, now this time my resistors are going to be in parallel. So one branch here. Good. अच्छा जी, तो अब हम लोग कहाँ हैं? ये रहा एक और रेजिस्टर पैरेलल में, ठीक है. एंड देन वी हैव एन एमीटर. एमीटर हम अभी नहीं बनाते, हम करंट की वजह से कर रहे हैं, लेकिन राइट. तो फॉर एग्जांपल मैंने एक एमीटर आई प्लेस्ड हियर, one ammeter I placed here, and one ammeter I placed here, right. For example, this is the type of circuit setup that I want you to imagine, right. Now what is happening is that my current is gonna flow, right. My current is gonna flow from here right? And then it's gonna get split here, right? So it's gonna split at, now this is what, this is a junction, right? We just studied that this is called a junction, right? So the current is gonna split from this junction, right? And for example, this is I1 and this is I2, right? And then later it's gonna combine to say give the same current, right? So here it's I1, here it's I2, but here it's still I, right? So the idea, what I'm trying to say is that basically we have the idea that I equal to I1 plus I2, right? This is what it means, right? So this was for your current, right? Now moving on. Potential difference, potential difference, okay. Okay, so when I'm going to talk about potential difference separate branches is the same, right? So this is basically what you need to know. Now when I'm saying this, basically, for example, if I look at the same circuit, right, and because I want to measure potential difference, I what like it will basically be different in this way, that I'll remove all the ammeters, right? I'll connect um a voltmeter. First of all, here I'll connect a voltmeter in parallel, right? Here I'll connect a voltmeter in parallel, and here I'll connect a voltmeter in parallel, right? So this is gonna be my sort of setup for seeing how potential difference is across a parallel circuit, right? So when that is going to happen, what I'll be able to see is that the potential difference across the whole circuit will be equal to the potential difference across each resistor, that we already know, right? That V, if I have V of the source, that will be equal to V1 and that will be equal to V2. This is the idea for a potential difference in a parallel circuit, right? So for example, this is V of the source, right? This reading will be V of the source, right? Voltage of the source. This reading here will be voltage across it, but it will be the same as this one, right? And this reading will also be the same as this one. So all of the readings are same. So the idea is that the potential difference across separate parallel branches is the same, right? So this is what you need to know for this one. Then we have the last one, which is not that bad actually. Okay, so resistance is that basically the reciprocal of the effective resistance parallel, which is basically 1 upon R, is equal to the sum individual resistances. Okay, so what do I mean by that, right? Now for this I need to do a little bit working, right? First of all, I know that I equal to V upon R. V upon R. I know this, right? And I know that if I'm talking about, I know that voltage is gonna be the same, right? So I'll not write V1, V2, I'll just simply write V because V is the same, right? So for example, if I'm saying I1, I know that I is not the same, right? I know that for what was for I. For I, it was that basically your basically your total current is equal to the current divided at the junctions, right? So basically your current is going to be something like this, that it's going to have that one thing, number thing here, right? So I1 is equal to V upon R1, because again resistance is also different, right? So this is the idea that you need to know, right? So for example, if I know firstly that I is equal to I1 plus I2, right? First of all. Secondly, I know that if I'm gonna replace something in place of I1, that is gonna be V upon R1 plus V upon R2, right? And yes, this is the first idea. And then yes, I can also write this I, which is on the left hand side, as V upon R, right? So V upon R total, for example, right? So let me write RT, right? So that is gonna be equal to the same thing which is written above. R1, right? This way. Now what I can do is I can take out V common, right? So when I'm gonna take V common out, I'll have what here? 1 upon R total. Is equal to, again I have V common, so it will be equal to 1 upon R1 plus 1 upon R2, right? So now I can easily cut off V because it's the same, right? So now what I'll have is 1 upon R is, like, R total is equal to 1 upon R1 plus 1 upon R2. Right, so this is how this derivation does come in paper, right? For resistance, you need to know how you're supposed to derive the thing. Right, now let me search for a question if I'm able to get one so that we can do it right now. Answers are not written anywhere, but still be able to do it, you know. Okay, yes, so we do have one worked example. Let's do it first ourselves and then see. Right, so for example, if I consider this example, a potential difference of 24 volt from a battery is applied to the network of resistors in figure 4.311a. What is the combined resistance of the 6 ohms and 12 ohms resistors in parallel? So if, you know, let's just consider we don't have this in front, right? Now let's see, right? So for example, when you have, you know, this, right, you can see that two of the resistors are in parallel and one resistor is in series, right? First of all, I'm gonna do what? I'm gonna calculate the resistance for this, right? So it's gonna be 1 upon 6 plus 1 upon 12, and then we'll take the reciprocal, right? So I don't have my calculator. Yes, I have my calculator. So let me first calculate it that, right? So it's gonna be, basically, don't make the, you know, habit of using 1 upon R equal to total. You just do direct reciprocal because that saves a lot of time, because you just need to add directly in calculator 1 upon 6 plus 1 upon 12, and over it the whole power is, basically you'll write 1 upon 6 bracket open, 1 upon 6 plus 1 upon 12 bracket close, to the power minus 1. This is what you're going to type in your calculator and you're going to get a direct answer, right? So I'm getting is 4 ohms, right? 4 ohms for this, right? For both of these, right? Now I have considered that I have a 4 ohms resistor replaced by both of these, right? So 4 ohms plus 8 ohms, 12 ohms overall resistance, right? And R1 they have given is 4 ohms. Combined resistance, they asked for the parallel ones only, so this is 4 for only these. Okay. Now, what is the current in the 8 ohms resistor? That R equal to total resistance of the circuit, 4 ohms. Okay, so they have basically solved it. and then they're asking what is the current. Okay, so this is a series circuit, right? So series circuit means that current at every point is the same. The total resistance, we know that R equal to V upon I, so your I equal to V upon R. The overall voltage here is 24 and overall resistance is going to be 4 plus 8, 12, right? So it's going to be simply 2, right? Do we have more questions? Okay, wait. We do have some questions, but we don't have the answers. But let's still do it. Okay, so we have some simple questions, but we're doing them just to solidify simple concepts. Now, for example, calculate the combined resistance R of a 1 ohm, 2 ohm, and 3 ohm resistor connected in series. So because all of them are connected in series, simply gonna add them, right? So 3, 2, 4, 5, 5, and 6, right? Then a 12-volt battery is connected across resistors. Calculate the current I flowing through each resistor. Okay, so we have a series, the resistors are connected in series, right? So the current at every point is going to be the same, and we know that overall resistance is 6 ohms, right? So R equal to V upon I. We know is 12, and your overall resistance is 6. So what is going to be 16 divided by 12 divided by 6? So that's giving me 2 amperes, right? Calculate the combined, what is the potential difference across each resistor? Okay, so when we're talking about in series, we know that voltage is not going to be the same. It is going to be V equal to V1, that thing, right? So now they're asking potential difference across each resistor, right? So now I'll calculate separately, right? Now how I'll do that? So I know that R equal to V upon I. V upon I. Right, so the voltage is going to be the same because no, the voltage is not going to be the same. R is, for example, when I'm calculating for 1 ohm resistor, right? So resistance is 1 and current is going to be the same, right? Current was 2 amperes, right? So for the first one is simply 2 volts, right? I wrote it 2 times. Right now, when I'm calculating for 2 ohms resistor, actually, so basically, right. So we have again R equal to V upon I. We are calculating potential difference. So potential difference is going to be IR, right? So I is going to be the same for everyone, for every resistor, right? So the only thing that is going to change is R, right? So here R is 2, right? So it's going to be 2 into 2 equal to 4 volts, right? And the same I'm going to do for my 3 ohms resistor, right? So for 3 ohms, it's gonna be, see, 3 into, again, I have 2 amperes. So that is gonna be that is gonna be 6 volts, right? So this is it, yes. Then we have calculate the combined resistance of 2 ohms and 3 ohm resistors connected in parallel. So I've already told you, what are you gonna type in calculator? Bracket open, right? You type 1 upon 2 plus 1 upon 3, right? And then bracket close, power minus 1, right? So this is giving me 1.2 ohms resistance is the answer for 2A part. Then we have a 12-volt battery is connected across the resistors. What is the potential difference across each resistor? We know potential difference is going to be the same, right? So R equal to V upon I. So overall resistance is 1.2 and overall current is what? Overall current is not known. Oh, sorry, they're asking for, no, they're asking for potential difference across each resistor. So you don't have to calculate, right? We know it's gonna be the same across each and everything, right? So it's gonna be 12 volt, the answer, right? Then calculate the current. Okay. So when I'm calculating the current, I should know that my voltage is gonna be the same, which is 12 volts. The only thing that is going to change is my distance, right? To 12 divided by 2 is 6, right? So 6 amperes will be for my 2 ohms resistor, and from my 3 ohms resistor it's going to be 12 divided by 3, so that is giving me 4 amperes, right? So this is how you need to simply solve them. Now comes the main topic of today. All of this part was pretty straightforward. Just need to simply look at the type of circuit and remember its properties and remember the derivation of series circuit resistance. Now comes the detailed part in which we need to discuss potential dividers. I'm gonna share the book with. Okay, wait now. Let's continue. Action and use of circuit components. Variable potential divider. So resistance of materials other than metals does not necessarily rise when the temperature increases, right? So, okay, this is one part that they're telling you, that resistance is not gonna necessarily rise when the temperature increases. Then what are the same? If a thermistor is part of a potential divider circuit, then its resistance decreases when the external temperature rises. So if resistance is decreasing when your temperature is rising, what are they saying? That one thing is decreasing, the other thing is increasing. So inverse relationship between both of them, right? The combined resistance of the two resistors then decreases. So if the supply voltage remains constant, the current in the circuit will increase. Okay. Supply voltage remains constant, the current in the circuit will increase. Right. Okay. This means that the potential difference across a fixed resistor increases relative to that across a thermistor. The potential difference across a fixed resistor could then be used to monitor temperature. A variable resistor can also be used as a potential divider. Moving the contact on the resistor changes the output of potential difference. Okay, so first of all, let's try to analyze this paragraph. So they're saying if a thermistor is part of a potential divider circuit, then its resistance decreases when the external temperature rises. So this I already told you, that resistance and temperature for a thermistor. Thermistor means that resistance is dependent on temperature for that particular resistor. The combined resistance of the two resistors, so we have one thermistor and we have one fixed resistor, right? The combined resistance of the two resistors then decreases, right? So when my resistance has decreased and when I have two of them connected in series, if they're connected in series, we're simply going to add them, right? So if one of the resistance has decreased, the overall resistance is also going to decrease because the sum is going to decrease, right? Now when the sum of resistance is going to decrease, we know that resistance is inversely proportional to the current, right? So if the total resistance is decreasing, so the total current will increase. That is what they mean, right? And another thing is that it can also be used as a potential divider. In the beginning of the class, I told you that potential divider is basically a line of resistors which are connected in series, something like this one, right? This is a potential divider because it's a line of resistors, because it's a line of resistors connected in series, right? And another thing that we know is that potential difference is used to provide a fraction of the voltage of the source to another part of the circuit, right? So what it's going to do is that it's going to provide a fraction of the voltage of the source, right? And now to calculate how it's doing that, we have a formula, we have a particular formula, right? Now the derivation and how this formula came into being is not a part of your syllabus, but the formula is simply is that we know that the current through the resistors, basically it's pretty simple also, that how are we going to derive the formula. See, when we're talking about the current, we know that first of all we're talking about a series circuit, right? So series circuit, if I'm talking about the overall current, right, I know my I is going to be the same, right? I know my I is going to be the same, right? So I am gonna simply use I for that, right? I know my resistance is the overall sum, right? So what I can write is R1 plus R2, and I know that overall voltage is going to be that of the supply voltage, right? So if I need to write about the total voltage, I can write voltage of the source, right? So this is what it looks like, right? This first thing, is because of this thing, right? Then so the voltage across R1, so now when I'm gonna bring R1 into the scenario, is it's gonna be, because if you're gonna divide according to the source, that basically it's consuming a part of, the source voltage. Basically we know, see, V1 is equal to I into R1, right? We know that it's a series circuit, so I is going to be the same, right? But the resistance is going to be a particular resistance, so we named it R1, right? And the voltage for a particular resistor is also going to be specific voltage, so we named it V1. But we know that our overall I is also equal to this thing, because we just looked at the formula. So what I did was I placed this thing here, right? So when I did that, I got this, right? I got this final formula, right? Same thing can happen for the other, um resistor, for R2, right? So basically the thing is that we have derived this formula, that if I want to calculate the voltage across a particular resistor, what I'm going to do is that I'm going to write down its resistance in the numerator, I'm going to write the overall resistance in the denominator, and I'm going to multiply it with the source voltage, right? This is my formula, and you will be required to use a formula in a lot of cases, so you are required to learn this formula, right? And you also know how it was derived, right? First of all, we started with current. We know that voltage is that of the source, so we simply named it V. We know that resistance is going to be the sum, so we named it R1 plus R2. We put this formula into that of a particular resistor, and we get that if we want to know the voltage across a particular resistor, then we need to do this, that we need to put that particular resistor's resistance in the numerator, put the sum in the denominator, and multiply with the overall source voltage, right? So this is the thing. And also the ratio of the voltages across the two resistors is this, right? So you can also calculate it if, for example, I know three things. I know V1, I know V2, I know voltage across this, I know voltage across this. Wait, let me bring it. Yes, I know voltage across this, I know voltage across this, I know one of its resistance, and I want to know one more resistance, so I can also use this formula, right? So yes, that's it for a potential divider. Okay, so these things aren't really, in that much detail. All you need to know about is that they have an inverse relationship with, the thermistor is going to have an inverse relationship with temperature, and LDR is gonna have an inverse relationship with light, right? That's all you need to know. But we're still going to do it so that we're on the safe side. So let's read through it. We have time. Now, thermistors and light-dependent resistors can be used as input sensors in a circuit to detect changes in the environment. Light-dependent resistor. The action of an LDR depends on the fact that the resistance of the semiconductor cadmium sulfide decreases as the intensity of the light falling on it increases. So again, we know that inverse relationship. An LDR and a circuit showing its action on are shown in figures 4.135. So where do we have an LDR? We have an LDR right here, right? Okay, and then what are they doing? Sometimes seen with a circle. When light from a lamp falls in the window of the LDR, its resistance decreases and the increased current lights the lamp, right? So basically, we have a circuit in which we have a bulb apparently. Yes, we have a bulb, right? So what's happening here is that when the light is going to fall, on our resistor, light dependent resistor, what's going to happen is resistance is going to, light has increased, right? So resistance is going to decrease, so current is going to be high, right? So when current is going to be high, bulb is going to light up, right? That's what's happening. Figure 4.13.15c shows how an LDR can be used to switch a relay, right? And we know that what was the relay doing? It was using a small current to operate a larger current, right? The LDR forms part of a potential divider across the 6-volt supply. Okay, we have two resistors lined up, so we have a potential divider, right? When light falls on the LDR, the resistance of the LDR, hence the voltage across it, decreases, right? So if the resistance fell, then the voltage also fell. There is a corresponding increase in the voltage across resistor R and the relay. And when the voltage across the relay coil, which is a high enough potential difference, okay, it acts as a switch and the normally open contacts close, allowing current to flow to the bell. Wait. corresponding increase in the voltage across resistor. Okay, so basically what's happening here is then when light is gonna fall on the LDR. Okay, now light has increased. Oh God. Okay, so light has increased. So what has decreased? Resistance has decreased, right? So if resistance has decreased, what has decreased? Voltage has decreased, because voltage and resistance are directly proportional, right? So because of that, now this LDR is consuming less voltage. So more of the voltage is going to what? More of the voltage is going to the relay and the across the relay and the resistor R, right? So because of that, what's going to happen is that basically a relay, if relay has a particular sort of structure in which basically we have two plates, you can say, and when a high enough potential difference is going to operate that particular switch which is within, basically this is what happens, right? Wait, let me show you if I can search for how a relay works. Wait, let me search for it. Okay. Okay. Okay, let's try to keep it simple and show you a simpler diagram. Wait. Right, so this is how it's working basically. This is the idea, right? So, okay, we went somewhere else, right? So this is how it's working basically. Now, see what's going to happen is when a large enough, when we have a large enough voltage, what's going to happen is that these two plates are going to attract each other, right? So when the control switch is turned on, current starts flowing through the coil. It generates a magnetic field around it, right? We know that around each and every current carrying conductor there is a magnetic field, right? So when current is going to flow through it, it's going to generate a magnetic field around it, and these two plates are going to attract each other and they're going to close, right? When contacts are going to close, current will be allowed to flow through it, right? When current will be allowed to flow through it, what is going to operate? Your bell is going to operate, right? Moving back to the book, right? This bell, current will be allowed to flow, and this bell is gonna, the current is gonna get to this bell, and the bell is gonna start working, right? So this is how it's working. Thermistor, a negative temperature coefficient thermistor contains semiconductor metallic oxides whose resistance decreases markedly when the temperature rises. So basically, why has it specified that it's a negative temperature coefficient? Because you actually have a positive temperature coefficient also, right? And what that means is that basically there are two types of thermistors. You have a negative coefficient thermistor, and you have a positive temperature coefficient thermistor. For a positive one, resistance is going to increase with increasing temperature, right? But for a negative one, resistance is going to decrease with increasing temperature, right? That's why. Shows one type of thermistor. Shows a symbol for a thermistor in a circuit to demonstrate how the thermistor works when the thermistor is heated with the matched lamp lights. Shows how a thermistor can be used to switch a relay. Okay, the same thing can be done for a thermistor, right? When it's gonna but what's gonna be the requirement for a thermistor to lower the voltage across it? Resistance should decrease, right? And when will resistance decrease? When temperature is gonna increase, right? See, it's written here. When the temperature rises, right? Okay, almost there. Relays. A switching current cannot supply much power to an appliance to a relay, so a relay is often included. This allows the small current provided by the switching current to control the larger current needed to operate a buzzer, as in a temperature operated switch or other device. Relays controlled by a switching circuit can also be used to switch on the main supply for electrical appliances in the home. In figure 4.3.17, if the output of the switching circuit is high, 5 volts, a small current flows to the relay, which closes the main switch. The relay also isolates the low voltage circuit from the high voltage. Okay. So basically here you can see a relay, here you can see, its contacts. And what it is doing is that basically we have an appliance right here, and what do we have here? What is this? This is the symbol of a resistor, right? So basically what it's doing is that we have a relay right here, and we just discussed what a relay is doing actually. It's operating a bigger circuit, which in this case, for example, was the bell. It was operating it using a smaller current, which operated a magnetic field within it. So right, so that's how it's working, right? Control the larger current needed to, okay, so control the larger current that we already did. Control by switching current can also be used to switch on the main supply. Yes, we know how it's going to switch on the main supply, right? Small current flows to the relay, which closes the main switch, right? And we know how those contacts closed because there was a magnetic field, right? Then we have light emitting diode. So an LED is a diode made from the semiconductor gallium arsenic phosphide. When forward biased with the cathode C connected to the negative terminal of the voltage supply, as shown in figure 4.3.1.8b, 1b, the current in it makes it emit red, yellow, or green light. No light is emitted on reverse bias. Okay, so basically first you need to understand what is forward bias and reverse bias. All of this detail is not required that much. We are covering all of this to be on the safer side, right? One I will see no question on it basically, right? But the thing is that question might come because it's still a part of syllabus, but they have not specified the detail you need to know, but it's still a part, right? So the thing is that when you're talking about forward bias in chemistry also, we studied that we connect the negative terminal to the, basically, for example, here what have they done, that the cathode is connected to the negative terminal, right? Now for example, when I'll connect the anode to the negative terminal instead, that is going to be reverse bias, right? Now in use, an LED must have a suitable resistor in series with it. Okay, to limit the current, so it should have a resistor to limit the current. What is going to happen when it's going to limit the current? Let's see. LEDs are used as indicator lamps in computers, radios, and other electronic equipment. Many clocks, calculators, video recorders, and measuring instruments of 7-segment red or green. Okay, each segment is an LED. Okay. Okay. Then finally we
हाँ,
have
बस
hmm
मैं कह रहा हूँ आज के लिए बस करें।
बस ये आखिरी बचा है, ये भी हमने पढ़ा हुआ है, ठीक है। इसमें बेसिकली क्या है, इसमें बेसिकली ये है कि अगर डायोड कंडक्ट्स व्हेन द एनोड गोस टू द पॉजिटिव टर्मिनल ऑफ द वोल्टेज सप्लाई एंड द कैथोड गोस टू द पॉजिटिव टर्म नेगेटिव टर्मिनल, यानी कि बेसिकली जो आपका बेसिकली योर पॉजिटिव टर्मिनल विल बी कनेक्टेड, positive terminal is anode, right? Anode will be connected to positive terminal of the battery, that will be forward biased, negative to negative, right? So that is forward biased, right? And we know that this is how it rectifies. For example, if I have an AC supply, so it would only allow voltage to flow half of the time, right? Right, so this is it for this, and this process is called rectification, right? So let's keep it till here now. Now we can end the class.